Hi, my name is Farah Zulaikha binti ROSSERI. Today, I'll be presenting our study which focuses on the growing concern of microplastic pollution in the water at Pantai Sungai Berembang, Kuala Perlis. Microplastics, which are tiny plastic particles, are increasingly found in aquatic environment around the world, and they pose significant risks to both ecosystem and public health. The objectives of our study are to determine the abundance of microplastic in the water at Pantai Sungai Berembang and to characterize the types of microplastics that are present in the area. So Kuala Perlis is well known for its fishing activities and rapid urbanization. However, these activities have raised concerns about the accumulations of microplastics in the environment, particularly through seafood consumption. Despite these concerns, there is currently a lack of specific data on the abundance and types of microplastics in Pantai Sungai Berembang. This gap in knowledge makes it difficult to fully understand the impact of microplastic on both the local ecosystem and public health. Through this study, we aim to highlight the extent of the problem and address the existing gaps in knowledge. To achieve our objectives, we employed two main methods. First, we conducted the sample collection by gathering water samples from the Pantai Sungai Berembang. Second, we carried out few steps in laboratory analysis to quantify the amount of microplastics present and classify the different types of microplastics found in the samples. Next, for the literature review, pollution driven by industrialization and urbanization significantly harms ecosystem, human health, and natural resources, according to Pontus et al. 2020. It disproportionately affects the communities, exposing them to higher levels of pollutants, according to Mukhopadhyay et al. 2022. Addressing these challenges requires integrated environmental and social approaches for sustainable and equitable health outcomes, according to Hundert et al. 2020. Next, for the water pollution caused by plastics, chemicals, and heavy metals threatens aquatic ecosystem and human health. Microplastics form from plastic debris, bioaccumulate in marine organisms, and disrupt ecosystem, eventually entering the human food chain, according to Lee et al. 2020A and Hundert et al. 2020. So the microplastics, defined as fragments smaller than 5 millimeters, come from degrading plastics and industrial products, according to La Rosa et al. 2021. These particles absorb pollutants such as heavy metals and organic compounds, amplifying their toxic effects on marine life and human through seafood. Lee et al. 2020b. So, microplastic pollution in seawater is particularly concerning. Extremely small particles nearing nanoscale pose toxic risks and to aquatic life and humans, according to Huang et al. 2020 and Prada et al. 2020. Humans, as major seafood consumers, face microplastics exposure risks, and these particles have also been found in tap water, sea salt, and bottled water, according to Saha et al. 2021. Research is needed to better understand their health impacts. Farah et al. 2020.
Hi, I'm SITI NURSHAHIRA and I'm excited to walk you through how we analyze microplastic from Pantai Sungai Berembang. Let's get started. Okay, first, let's talk about the materials we use. We use stainless steel sieve with mesh size of 1 mm and 0.355 mm for filtering, along with distilled water, 0.5 ferrous sulfate solution at 30% hydrogen peroxide for chemical processing. We also use aluminum foil and filter paper to handle the samples. For sampling, we choose Pantai Sungai Berembang as our study area, a coastal location affected by urban and rural activities, making it a hotspot for microplastic pollution. We took water samples from 3 sites using 1 liter plankton net and stored them in labeled glass jars. After sampling, we move on to wet sieving. We pour the samples through the sieve and rinsing with distilled water to ensure no microplastic were missed. The solids retained were collected for further analysis. Next, we determine the mass of the solids. We transferred them into pre-weigh beakers, dry them at 90 degrees Celsius for 24 hours, and weigh them again. The mass was calculated using the formula B minus A is equal to C. Then came density separation. This step involved isolating microplastics using a density separator. The microplastics were trapped on filter paper, covered with aluminum foil, and left to dry overnight. By the next day, they are ready for analysis. Finally, we examine the dry microplastics particles under a dissecting microscope with 40x magnification. We identify their shapes and sizes, carefully couch them, and weight them for further study. This step confirms the presence of microplastic in our samples.
That concludes the method section. Just to clarify, in step 5, I forgot to mention that after determining the mass of the solid, we perform wet peroxide oxidation to remove organic material. The solids were treated with ferrous sulfate solution and hydrogen peroxide, heated to 75 degrees Celsius, then cooled to separate the microplastics.
My name is BINTI ROSLI, and in this section, I will be discussing about the total solid mass of microplastic collected from 3 different sites based on their sizes. As shown in table 1, we have analyzed samples from 3 different sites, with the microplastic sizes categorized using the sieve of 0.355mm and 1ml. For sample 1, the total solid mass of microplastic with the size of 1ml has a higher mass than 0.355mm. In sample 2, the total solid mass increases, but still the 1mm mass is slightly higher than the 0.355mm. Finally, in sample 3, microplastic mass of 0.355mm is 0.0225 grams. And for the 1mm size, we observe the most highest mass, which is 0.6279 grams, which could suggest a higher contamination levels at this site. From these findings, we can conclude the larger microplastic particles generally have a higher total solid masses across all sites. Moving on to the shapes of microplastic found in sample 1. For the total microplastic found in sample 1 is 18 instances. For the 1mm sieve, we observe the total of 4 fiber strands, 3 triangular shapes, 2 rectangular shapes, and 2 fragments. This indicates the larger microplastic are most likely to maintain their distinct shapes. For the 0.355mm sieve, includes 2 fiber strands, 4 fragments, and 1 bead. Moving on to the shapes found in sample 2. In sample 2, we found a total of 21 instances of microplastic particles in the sample. Within the 1mm sieve, we found the 3 triangle shape, 3 rectangle shapes, 2 fragments, 2 films, and 2 beads. For the 3.55mm, we found a total of 1 fiber strands, 3 fragments, 1 beads, and 3 films. Lastly, the shapes found in sample 3. Sample 3 had the most microplastic particles than the other 2, totaling up to 28 instances of microplastic. For the 1mm sieve, we found 2 triangles, 6 fragments, and 6 films shapes. And for the 0.355mm, we found a total of 2 fiber strands, 6 fragments, 1 triangular, and 5 films shape. Next, I will be discussing the total of microplastic based on the shape found as shown in table 2. The data was summarized into a pie chart on the left. The pie chart shows that fragments had the most highest percentage, that is 34%, followed by film, fibers, triangular, and rectangular. And lastly, the most least percentage is beads with the percentage of 6%. Lastly, I will be discussing the average number of microplastic in all study area. For the microplastic with the size of 1mm, the average number found across all study area is 12.67 plus minus 1.53, indicating a relatively high presence of larger microplastic particles. On the other hand, for the smaller microplastic with the size of 0.355mm, the average number is 9.67 plus minus 3.79, showing a slightly lower concentration compared to the 1mm particles. These findings suggest that a larger microplastic tend to be more easier to detect than the smaller microplastics.
This study achieved its objective by determining the abundance and characterizing microplastics in water at Pantai Sungai Berembang, Kuala Perlis. Microplastics were found at all 3 sites, with Site 3 showing the highest abundance, followed by Site 2 and Site 1 for both sizes of 1mm and 0.355mm. For 1mm particles, fragments were the most common shape, followed by films, triangles, rectangles, fiber strands, and beads. For 0.355mm particles, Fragments were also most common, followed by films, fiber strands, beads, and triangle. A total of 67 microplastics were analyzed. Variation in concentration reflect human activity and environmental conditions. Characterizing microplastic helps understand pollution composition. Future research should use FTIR to identify functional groups in microplastic for better classification and ecological impact assessment.